So we're going to practice doing some drawings. So we've got volume, temperature, pressure, moles. Tell me which two you want to compare. What two variables up there you want to compare? What do you want? Volume and temperature. So we're going to compare volume and temperature. Okay? So pressure and the number of moles have to stay constant. Okay? So we're going to go ahead and how should we draw? We'll draw, which one do you want to change? What do you think would be easier to change, volume or temperature?
Volume.
Okay, volume. So you guys draw two containers. How should we, the two containers have to be different sizes, so how big or small, do you want to draw something in relative size to that one? How do you want to draw, bigger or smaller?
Super small.
Super small, okay? Now, before we draw it smaller, what do we have to put in there to show the moles? So we just put, how many do we want to put in?
4.
4? Okay. All right. What should we do with the temperature? How would we show the temperature on those? What's that?
With arrows?
Yep, with arrows. So we'll draw arrows. Same size arrows. All different directions. Okay. So I got 4 of them. Okay, so I'm trying to think how this is going to work here. So pressure needs to remain constant. So when we draw our second one, we're going to have to keep pressure constant. So let's write a pressure above this. What kind of pressure do you want to write above it? Just any type of unit of pressure.
1 atmosphere.
There we go. I like that. I like the way you're thinking. 1 atmosphere. Okay. So we say it has 1 atmosphere of pressure. So it's when it's hitting the size of the container, it's 1 atmosphere of pressure. Okay. So we're going to decrease the volume. You say make it smaller, right?
Yeah.
All right. This one's going to be hard for me to show. But maybe you can show it a little bit better. Okay. Now, the volume gets less. Now, what do we know about the pressure? It has to be the same, right?
Yeah.
1 atm. The moles are the same. What do you think is going to happen to the size of the arrows? Are they going to stay the same? To keep the same pressure?
Maybe small.
They've got to be smaller, right?
Yeah.
Does that make sense?
Yeah.
Because what do we know? What do we have to know about the collisions? The number of collisions. If we put it in a smaller space, if it's the same temperature, the pressure is going to go up, right? Because you're going to have a lot more collisions. So we've got to make the arrow smaller. I don't know how you do that on yours, but you can make it smaller. But as long as you you can make it better than I can, because I don't have much control over this guy here. But I would make it smaller, right? In proportion to that. So let's say that how many of these boxes do you think fit in this one over here? How many times do you think that would go in there?
6.
6? Okay. So I mean it's just an estimate, so be about like that, right?
Yeah.
All right. So we can say 6. We're just playing around with it. So the size is 1/6 volume. What do you think's going to happen to the temperature then?
It's not even
1/6 the temperature, right?
Yeah.
Does that make sense?
Mm-hmm.
So it's be 1/6. So if this over here is 300 Kelvin, to get the same pressure in a smaller container, what does the temperature have to be over here? 50 Kelvin. You got to really cool it down to get the same pressure. Any questions on that? Does that make sense? So we would call that a direct relationship. We would say that temperature and volume are, they move the same way. If the volume increases, keeping the same pressure and number of molecules, it has to be directly proportional. Good? All right. All right, let's do our next one here. Okay? So we got volume, temperature, pressure, and moles. So which one here do we want to compare? Eric, which one do you want to compare?
Moles and pressure.
Okay, moles and pressure. All right. So these are constant. So I'm going to let you guys go ahead and do that. So keep volume and temperature. So let's use 4 molecules together. 4 molecules again, and go ahead and draw boxes.
But we have to do 4 molecules. But
No, you can do more if you want to.
because moles are changing.
Oh, yeah. Well, at least the first one, we want to do all the same. So how many do you want to do in the first one?
Mm.
Let's go with 6. So do 6 in the first one. And the boxes have to be the same size, right? About. I mean, they should be identical because we want to keep that constant. So the volumes of the boxes should be comparatively same size. The temperature has to remain constant, so we've got 6 in here. And then the size of the arrow would be the same in all of them, right? Okay. So what do you know about the other one? What do you want to do with the other one? Because which one would be easier to change, to show a change of, moles or pressure?
Moles.
Moles. So what do you want to do on the other one? How many do you want in the other one?
4.
4?
Yeah.
Okay. And will the arrows be the same size?
No.
Yeah.
Should be the same. Constant T.
Oh, yeah, no.
That's okay. So the arrow should be the same. Okay. Now, you guys would have been better off choosing 3, but I'll let you do 2. Okay. So, we know the pressure goes down, right? Okay. So the moles are decreased, so the pressure goes down, and that's a direct relationship, right? Okay. Does anybody? Let's go ahead and put initial pressure here. What do you want to put down here as a pressure? Let's go 1 atm. Does anybody want to guess at the pressure over here? I bet you can get it. See if you can solve for it. What's the pressure on that one on that right side? Go ahead and solve for it.
Is it going to be 2/3? Or
Yeah.
2?
Yeah,
2/3.
it's 2/3, right? That's why I said if I had half the number, it would have been
Just been
half.
But
So this would be 0.67, right? Make sense? So what we're doing is we're doing the laws. You didn't know it. We're doing the laws. So these are directly related. So the first one, if you show, hey, what's a direct relationship?
so volume and temperature.
So how do you show in an equation a direct relationship between volume and temperature? Here it is. V over T equals V over T. This V over that T, okay? And let's say that this volume here was 6. And this was 1/6. This would be 1 liter, let's say. So I'm adding a little bit more. So that would be 6 over 300, right? That's the same as what? This should be a T. I don't know why I put T. T2 is supposed to be. So that would be a T. So the volume is 1, and that's 50. You get the same answer out? 1 over 300 is the same as 1 over 50, right? Okay, so this is V over T. This one should be pressure over N equals pressure over N. So this is 1. And the number of moles we have is 6. Okay? So then this is 0.67.
Is N moles?
N would be moles. And that would be 0.67, and this would be 4. Does that give you 1/6? 0.67 divided by 4 should give you 1/6, right? Or it should give you, what is 1/6? Is that like point?
1.6666.
Yeah, that's it. 1/6 is 0.166.
And then 0.67 divided by 4 is 0.167.
There you go. So there you go. So then we, all right. Now let's do our last one. Let's try to get one. The relationship is inverted. Okay. So last one we'll do. So we got VT, PV, and so we're going to have to pick one of these when we compare them. They're going to be inverse of one another. So we've done temperature and volume. We've done pressure and moles. They've been directly related. We want to do one that's inverse related. Which one do you think, when we change one, the other one is goes up? When we change one it goes down, the other one goes up. Which
moles
one?
and temperature.
Oh, I messed up on this one. Okay. And if we did that one, moles and temperature.
I'm trying to think.
Would it be pressure or temperature?
Pressure and temperature. So when you increase the temperature, does the pressure increase on a constant volume?
Because it hits
Yeah.
Okay, so that wouldn't be it.
tough. This is tough. You increase the moles, you increase the volume, so it's not that either.
Is it?
What the heck?
There's two of them there. If we
Volume
compare.
and pressure?
Okay, so let's go volume and pressure. So we'll create our volume, and then so volume and pressure. So temperature needs to be constant, and moles need to be constant. All right, so moles we'll do 4, and the arrow's the same length, right? Okay, so then the volume, what do you want to do, bigger or smaller?
Bigger.
Bigger, okay, let's go bigger. So we'll go about twice as big. Okay, so, and then we've got same number here, right? Same arrow, right? Length. Pressure, pressure's hard to show. So if we made this one 1 atmosphere, now let's make this 2 atmospheres. What's the pressure over there?
If it's twice as big, then it's going to be 1 atmosphere.
It's 1 atmosphere. So, twice as much space for the molecules to go. Twice as much space means half the collision. So then, it's 1 atmosphere. So when you set up your equation, it would be P times V equals P times V are equal. Okay? So we'll say that this is 1 liter and this is 2 liters. So 2 atmospheres times 1 liter equals 1 atmosphere times 2 liters.
That's pretty fancy.
Okay, so the laws are these, and I'm going to have you write them down before we go, but basically we just did the laws. That's all we did. We say if we remain, 2 things can remain constant. So I'm just going to give you 2 laws. And you can get all the laws from these 2 laws. So the first one is called the combined gas law. And it combines. All right? So it combines Boyle's, Charles, and Gay-Lussac's are all combined in what's called the combined gas law. Pretty nifty they came up with that, right? Combined gas law. So P times V equals P times V. That's 1, 1, 2, 2. Okay, Charles' law is V over T equals V over T. And they say that they're directly related. And Gay-Lussac's law says P over T equals P over T. So they say all of these we can make into P1 times V1 over T1 equals P2 V2 over T2. That's the one you have to know. Right?
Combined is one.
Yes, because what you can do, if it says something remains constant, you can cross it out of your equation. So if they say temperature remains constant, what do?
On the test, will we have to know like Boyle's compared?
I don't think so. I don't think you guys are past that point where I'm going to have you memorize who goes with what. I just don't think that's necessary.
Okay. Thank you.
Uh-huh. And so if you say volume remains constant, you cross it out because they're going to cancel out anyway. The other law involves moles, and that is called the overall law that includes moles would be called the ideal gas law. Now the ideal gas law is PV equals nRT, and we got this R in there, and that R is going to be 0.0821 if it's measured in atmospheres. Okay, it's 8.31 if it's kPa that you're using as your pressure. That's the only thing that changes. And then it's
8.31 you said?
Yep, it's kilopascals. And then 62.4 is if it's in millimeters of mercury. So that's the R values. If you use pressure as one of those 3, you'll have to use whatever constant goes with that pressure.
Do you have to memorize all 3 of those R's?
No, I give you those.
Okay.
I give you the equations too.
Awesome.
Okay. What's the last thing I was going to? Oh, temperature has to be in Kelvin. So if it's in Celsius and you got like 20 degrees Celsius, and you got to convert it to Kelvin, you guys remember what you do?
You add 273?
Add 273. Okay. So then when you're going Kelvin is always going to equal degrees Celsius plus 273. That's how you solve for Kelvin. So you just always add it. And every law, you have to use Kelvin. Can't use Celsius. Okay. And then the last law that's not in the combined gas law that I need to show you would be in...
Wait, is this a third law or is this part of
I'll do that tomorrow. We're running out of time. Okay. So that's a lot of information at once, and then tomorrow we'll just work on problems.
That wasn't too bad.
Does that make sense, the way they're kind of drawn out?
Yeah.
Yeah.
Okay, good. Now, I think